Okay, so the topic for this week and for most of next week as well is going to be about heat cycles. And these describe the processes whereby you can change the state of a thermodynamic system in a cycle. So that means you go round and round in the same changes of state. And by doing this, you can do something useful. So by making the system go round in a cycle, you can produce work. And I showed you an example of this in the first lecture, right? This is a Stirling engine. This is an example of a heat cycle. The system goes round and round in a given way, and by doing this, it is able to generate some energy, generate some work. Okay. So by the end of the next 2 weeks, we should be able to describe how something like this works. Okay. So I'm going to imagine a very simple system just to explain things, and it's the one we've looked at before. Suppose that you've got this gas here, which is thermally isolated. Okay. And you're controlling the pressure with this piston, which applies a certain amount of force to the gas. So we've got this gas. We'll say it's got a volume V, and it's got a pressure equal to P. Okay. Now, if I draw this in a bit more three-dimensionally, which is always tricky, of course. So I've got a box, and I've got the piston inside the box like this, which is the forces being pushed down on the piston. And inside of there, I've got the gas. Now, I want to look at what happens when the gas expands. So suppose the gas expands by an amount of volume delta V. If I draw this on this diagram here, so beneath here I've got the gas, and the gas expands a bit, so let's say it expands by this amount. Okay. So this is delta V. Okay. That means a change in length here, which I can call delta L. And we can assume that this piston here, the top of the box, has an area equal to A. So we can say some things in this case. Well, first of all, the pressure is defined as force per unit area, right? So if the force is F and the area of the top of the box is A, then the pressure is simply F divided by A. And the expansion in volume, delta V, is equal again to the area times the amount by which the piston is moved. So those are simple equations. So the question I want to ask is how much work is done by the gas in this case? The gas is expanding, it's pushing against the piston, it's pushing the piston up, therefore it's doing work. It's giving energy to whatever is attached to the piston. So we can calculate how much work it does, how much energy. So the change in work done by the gas, delta W, let's call it. Well, work done is defined as force times the distance moved, right? So by definition, this is force times the height by which the piston is increased. That's F delta L. Okay. But now I can use these two equations above. First of all, I can write force is equal to pressure times area. And then secondly, I can write delta L is equal to delta V divided by area. And you see that the areas cancel, and therefore you conclude that the work done by the gas is equal to the pressure of the gas times by its increase in volume. Now, in this case, we've imagined that the volume only changes by a very small amount, but over a whole cycle, obviously, the volume can change quite a lot, and the pressure can also change as a function of volume. So in general, to get the general expression for work, we need to integrate this equation over lots of small steps. So if the gas goes from volume V1 to volume V2 with the pressure P, which can depend upon the volume of the gas, in this case, then the work done W is given by the integral of these small amounts. So in other words, the work done is the integral from the initial volume to the final volume of P of V dV. So that's a central equation in working out how these heat cycles work. Okay, right. So this leads us on to what is known as the first law of thermodynamics. I'm going to run out of space. Fortunately, there we go. Okay, so I've got this gas in the box, right? This gas has a certain amount of energy which is equal to U. We call U the energy of the gas. Now, how can the energy of the gas change? There are two ways it can change. Firstly, you can heat the gas. So you can put in heat, Q, right? I can put a fire under this box, increase the temperature of the gas, and that will increase the energy of the gas. Right? Another way you can change the energy of the gas is in the case we've just discussed. If the gas is expanded or contracted, then the gas is doing work, and therefore it's gaining or losing energy. Okay? So, again, by moving this piston up or down, the gas can do work, which is W. Now, once we've defined this, the first law of thermodynamics says something very simple. If the energy is U, and the only way you can change the energies is either by doing work or by putting heat in, then the change in U must be equal to the amount of heat you put in minus the amount of work the gas does, okay? Just to conserve energy. So we can write this symbolically in the following way. Delta U is equal to Q minus W. So I've explained in words, so let me write what each of these terms is. This is the change in internal energy of a system, I should say, I think. The system can be a gas as I've drawn it, but it can be anything. Right? Any system, we can use this equation. Q is the heat going into the system and W is the work done by the system. So it's just a statement of conservation of energy. If I put heat energy into the system and I take work energy in the form of work out of the system, then the difference between these two will be the total change in energy. It's just conservation of energy. Important words here, the heat going into the system is positive. So if I put heat into the system, it's plus Q. If I take heat out of the system, it's minus Q. The work done by the system is positive. So if the system does work, so it pushes the piston, then this is plus W. If the piston is pushing the gas down, then this would be negative work, minus W. So in this class, I'm only going to talk about a very simple system. And then we're going to generalize this next week to more complicated things. But this simple system will show all of the important behaviors. Okay? And it's very similar to the system we always looked at so far. So I have this gas, which is thermally isolated. Force F. And then I'm going to put this gas on something which is known as a reservoir. Which just means that I can fix the temperature. Okay? So a reservoir means I can hold exactly constant the temperature of this box here, and thereby change the temperature of the gas. Now, I imagine that I can control the force on the piston, and by controlling the force, I can control the pressure, and I can control the temperature as well. Okay, so we control pressure of gas by changing the force F, and we control the temperature of the gas by the reservoir. So we imagine we have complete control of this system. Okay, so I'm going to talk about, so we can control the system in different ways. For example, I can increase the force F and push the gas down, or I can decrease the force F and let the gas expand. I can increase the temperature and thereby increase the pressure, or I can decrease the temperature and thereby decrease the pressure. So I have complete control of this system. Okay. And I want to talk about the 3 different ways in which we can let the gas expand. So 3 types of expansion. Which again are going to be important when we talk about the theory of heat cycles. So the first type of expansion I want to talk about is the simplest and is called isobaric expansion. Okay. Isobaric is from the Latin or Greek or something. It's simplest to remember, this is the expansion for which the pressure is a constant. So in this case, what we do is we slowly increase the temperature on the reservoir, okay? But we keep F a constant. In this case, as we increase the temperature, heat will go from the reservoir into the gas. That will increase the pressure of the gas, and the increased pressure of the gas will push the piston up. Okay? So in this case, we increase temperature T, we hold the force and therefore the pressure a constant. So I can plot the behavior of the system on what's known as a pressure-volume diagram. So we put pressure at the top, volume at the bottom. So we start at some certain volume V1. We end up at some other volume V2. Now in this case, because we hold the force constant, the pressure is a constant. So if I start there and I end up here, then we just move in a straight horizontal line on this diagram. So if I draw that in pictures, that corresponds to going from a case here, where we have the gas like this, at temperature T1. We put heat into the gas, and by doing so, we end up, keep the force the same, we end up with an expanded gas at a higher temperature T2. So this kind of expansion is known as an isobaric expansion. Okay. The second type of expansion I want to talk about is called isothermal. And again, simply this means that we hold the temperature a constant. So in this case, we hold the temperature a constant, but we reduce the force on the piston. So as we reduce the force on the piston, that reduces the pressure, and that lifts the piston up. So that's another kind of expansion. Okay. So here we reduce the force, and we hold the temperature constant. Okay, and if I do the same as I did the isobaric expansion, that looks like this. You start with pressure volume V1. You end up with volume V2. But because you've reduced the force, the pressure is now less. You've reduced the force on the piston, so the pressure of the gas is now less, and therefore you move down in a curve, something like this. So if I draw the same thing in pictures, then you start off with this compressed gas with a force F1 and temperature T, and you end up with the same temperature T, but you reduce the force and allow the gas to expand to force F2. Okay? And in this case, F1 is greater than F2, so the force is reduced. The final type of expansion is similar to isothermal. In this case, again, we reduce the force and allow the gas to expand, but instead of attaching it to the reservoir, we block it off from the reservoir. So we completely thermally isolate the gas, no heat can go in or out, but we let it expand in the same way. Now this kind of expansion is known as an adiabatic expansion. Adiabatic, and the point of an adiabatic expansion is that no heat is transferred. So heat does not go in or out. So you reduce F and thermally isolate the gas. So you do not allow heat to flow either into or out of the gas in this case. Okay? Now, in terms of a pressure volume diagram, it looks very similar to the isothermal case. I'll explain what the difference is in a moment. So you started off here, and you end up somewhere down here, and again it's a curve which goes something like this. What's happening in terms of the pictures, though, is we thermally isolate it, so no heat can flow inside or out of the gas. You start with pressure F1 here, sorry, force F1, and we go reduce the force F2 and allow it to expand. Okay. Now, in this case, the temperature of the gas does change. Okay. The temperature of the gas changes because as it expands, it's doing work. Okay. So it's using energy to push the piston up. And as it uses that energy, the temperature of the gas goes down. Okay? So because it's using energy to expand, the temperature of the gas goes down. So if we say again temperatures T1 and T2, then we have that the force is reduced, so F1 is greater than F2 prime. I say prime because it's different from that. And also, the temperature has reduced. Okay. Temperature is reduced because the gas has done work. It's used energy to push up the piston. So that energy results in the gas being cooler. Okay. So although the shape in the pressure volume diagram is similar to the isothermal case, it loses temperature. It gets colder, and that means at the same volume it has a lower pressure. So if I were to draw the isothermal case, that looks something like this for reference. Okay. So the adiabatic has a similar shape to the isothermal expansion, but it lies lower on the diagram. Okay. And it lies lower because it is using energy which is not replenished from the reservoir, and therefore the pressure drops. Okay. So we've seen three types of expansion there. The isobaric is just at constant pressure, the isothermal where you hold the temperature constant, and then finally adiabatic where you do not allow heat to flow. These are idealized expansion procedures. Okay, and I want to finish with a couple of notes, and then I think we'll probably take a break. Okay, so just two notes. The first is that for the adiabatic, you've got that Q is equal to 0, and in this case, the first law of thermodynamics tells you that the change in internal energy is simply minus the work done. Okay. So the first law says delta U is Q minus W, but Q is 0, so it's just minus W. The second point explains why these PV diagrams are useful. If you look at the form of the work done, we defined it as the integral from V1 to V2 of P dV. So I start off somewhere at V1, and I end up somewhere V2, and I have some kind of expansion process between them. Can be complicated in real life, of course. Then what is this integral? The integral of P dV is simply the area under this curve in the graph. So the work done in the pressure volume diagram is the area under the expansion curve. So that gives a geometrical interpretation of the work done. It's the area contained under the curve. Right? So if we looked at those three kinds of expansions we had, the first was isobaric, the next one was isothermal, and the final one was adiabatic. So the work done in each expansion is given by the area under the curve. So you can see that the isobaric process, constant pressure, does the most work. This is highest, so the area is the most. So isobaric does the most work, then isothermal, and then finally adiabatic does the least work, because it's lowest.